Welcome friends. Let us continue with our topics in differential geometry. In the last session, we have seen Gauss-Bonnet theorem and various results in geodesic coordinate system. In this session, let us begin our discussion with isometries. Isometries and spaces of constant curvature. Let M1 and M2 be smooth oriented Reimannian two manifolds. Suppose f from M1 to M2 is an isometry that preserves the orientation. Thus, f is smooth, injective, surjective, and it has a smooth inverse. Moreover, df preserves the inner product on tangent spaces. Inner product dfv1 dfv2 is equal to inner product v1 v2 for v1 v2 element of T of M1 M1, where small m1 is an element of capital M1, and if tau is any two form giving the orientation of M2, then f star tau gives the orientation of M1. Note that since f preserves the Reimannian structure and the orientation, f preserves everything defined in terms of these. For example, the curvature, the Reimannian connection, and the parallel translation. 5 explicit statements are given. First one, f induces a map f tilde from S of M1 to S of M2 defined by f tilde of M1V is equal to Fm1 dfv, where M1V is an element of S of M1. This map is smooth and has a smooth inverse, namely f tilde inverse is equal to f inverse tilde. Note that pi 2 composite f tilde is equal to f composite pi 1. We can see the map f tilde is from S of M1 to S of M2 and pi 1 is from S of M1 to M1 and pi 2 is from S of M2 to M2. Moreover, since df is an orientation preserving isometry at each point, f tilde of g M1V is equal to g f tilde of M1V for all M1V element of S of M1 and g element of S1. That is, f tilde composite g is equal to g composite f tilde for each g element of S1. Second one, f tilde preserves the forms omega 1, omega 2 and psi, where psi is the one form of the Reimannian connection. For if T is an element of T of Sm1 M1V, then f tilde star omega 1 raised to M2 T is equal to omega 1 raised to M2 d f tilde of T, that is equal to the inner product dfv d pi 2 df tilde T, which is equal to the inner product dfv df of d pi 1 T, which is equal to the inner product v d pi 1 T, which is equal to omega 1 raised to M1 T. That is, f tilde star omega 1 raised to M2 is equal to omega 1 raised to M1. Similarly, f tilde star omega 2 raised to M2 is equal to omega 2 raised to M1. To check the connection is preserved, we use the uniqueness of the Reimannian connection. Note that f tilde psi raised to M2 is a connection form on S of M1, since f tilde star psi raised to M2 of V is equal to psi raised to M2 d f tilde of V, which is equal to psi raised to M2 V, which is equal to 1. G star f tilde star psi raised to M2 is equal to G star composite f tilde star psi raised to M2, which is equal to f tilde composite G star psi raised to M2, which is equal to G composite f tilde star psi raised to M2, which is in turn equal to f tilde star g star psi raised to M2, which is equal to f tilde star psi raised to M2 for each g element of S1. Moreover, d omega 1 raised to M2 is equal to psi raised to M2 meet omega 2 raised to M2, and d omega 2 raised to M2 is equal to minus psi raised to M2 meet omega 1 raised to M2. So that d omega 1 raised to M1 is equal to d of f tilde star omega 1 raised to M2, which is equal to f tilde star d omega 1 raised to M2, which is equal to f tilde star psi raised to M2 meet f tilde star omega 2 raised to M2, which is equal to f tilde star psi raised to M2 meet omega 2 raised to M1. Similarly, d omega 2 raised to M1 is equal to d f tilde star omega 2 raised to M2, which is equal to f tilde star d omega 2 raised to M2, which is equal to minus f tilde star psi raised to M2 meet f tilde star omega 1 raised to M2, which is in turn equal to f tilde star psi raised to M2 meet omega 1 raised to M1. Thus, the connection form f tilde star psi raised to M2 satisfies the simplified form of the structural equations. By uniqueness, f tilde star psi raised to m2 is equal to psi raised to m1. Third one, f preserves curvature, that is f star k raised to m2 is equal to psi raised to m1. 4. d psi raised to mi is equal to minus k raised to mi composite pi I omega 1 raised to mi meet omega 2 raised to mi for I equal to 1 and 2. So that minus k raised to m1 composite pi 1 omega 1 raised to m1 meet omega 2 raised to m1, which is equal to d psi raised to m1 equal to d of f tilde star psi raised to m2, which is equal to f tilde star minus k raised to m2 composite pi 2 omega 1 raised to m2 meet omega 2 raised to m2 minus k raised to m2 composite pi 2 composite f tilde into f tilde star omega 1 raised to m2 meet f tilde star omega 2 raised to m2, which is in turn equal to minus k raised to m2 composite f composite pi 1 omega 1 raised to m1 meet omega 2 raised to m1. Hence, k raised to m1 composite pi 1 is equal to k raised to m2 composite f composite pi 1, that is k raised to m1 is equal to k raised to m2 composite f, which is equal to f star k raised to m2. Fourth one, f preserves parallel translation, that is if alpha is a map from closed interval ab to m1, then the horizontal lift f composite alpha tilde of f of alpha through f of alpha of a d f of v is given by f of alpha tilde is equal to f tilde composite alpha tilde, where alpha tilde is the horizontal lift of alpha through alpha of a v. The reason is that f tilde star psi raised to m2 is equal to psi raised to m1 and d f tilde k raised to m1 is equal to k raised to m2. Fifth one, f maps geodesics into geodesics. For alpha is a geodesic if and only if alpha dot is parallel along alpha. Note that given M, the set of all orientation preserving isometries H from M to M forms a group K under composition. We call this group K the group of isometries of M. Definition: K is transitive if for each M1 M2 element of capital M there exists H element of K such that H of M1 is equal to M2. We will move on to a theorem. Theorem 1. Let M be a smooth oriented Riemannian 2 manifold. Suppose the group of isometries of M is transitive, then M has constant curvature. Proof is like this. Let M0 is an element of capital M. Then for any M in M, there exists H element of K such that H of M0 is equal to M. Thus, K of M0 is equal to H star K of M0, which is equal to K of H M0, which is equal to K of M. Isotropy group. Definition: let K denote the group of isometries of M. For M0 element of M, let K M0 denote the subgroup of K leaving M0 fixed. That is, K M0 is H element of K such that H of M0 is equal to M0. K M0 is called the isotropy group of M at M0. Note that for K element of K M0, dk from T of M M0 to T of M M0 is an orientation preserving isometry. That is, dk is a rotation of T of M comma M0. Thus, for each K element of K M0, there exists G element of S1 such that dk of V is equal to GV for all V element of T of M M0. Moreover, since d of K1 composite K2 is equal to dk1 composite dk2, the map phi from K of M0 to S1 defined by K goes to dk of M0 is a homomorphism. Now, let us see a lemma on this homomorphism. Lemma: if M is connected, the homomorphism phi from K M0 to S1 is injective. Proof: let G from d epsilon to M be a geodesic coordinate system about M0. Note that for K element of K M0, G of d epsilon goes to G of d epsilon since K is an isometry. Moreover, G inverse composite K composite G is an orientation preserving isometry of d epsilon leaving 0 fixed. That is, G inverse composite K composite G is equal to small g for some rotation G element of S1. Since dg of 0 is also a rotation by G, dk M0 is equal to d of G composite small g composite G inverse M0 which is equal to dg composite g composite dg inverse of m naught. Thus, K is an element of kernel phi if and only if dk m naught is equal to identity, if and only if g is equal to the identity, if and only if K given g of d epsilon is equal to g composite small g composite g inverse equal to identity. Thus, if K is an element of kernel phi, the set n equal to m element of m such that Km equal to m and dk from T of mm to T of mm is equal to identity is an open set in M. On the other hand, since K and dk are continuous, n is closed in M. Since M is connected, n is equal to M, that is K is equal to identity on M. Thus, kernel phi is equal to identity and phi is injective. Now, let us move on to another theorem. Theorem 2. Let M be a connected oriented Riemannian 2 manifold. Suppose K1 is a subgroup of the group K of isometries of M such that first one K1 is transitive and 2 for some m naught element of capital M, the homomorphism phi from K1 m naught to S1 is surjective, where K1 m naught is equal to Km naught intersection K1, then K is equal to K1. Proof. Suppose H is an element of K. By transitivity of K1, there exists H1 element of K1 such that H1 of Hm naught is equal to m naught. Then H1H is an element of Km naught. Since phi given K1 m naught is surjective, there exists K1 element of K1 m naught such that phi of K1 is equal to phi of H1H. Since phi is injective, by the lemma K1 is equal to H1H, that is H is equal to K1 H1 inverse, which is an element of K1. Thus, K is a subset of K1, that is K is equal to K1. Definition. For each small m element of capital M, the set Km is equal to K of M, where K is an element of Km naught, is called the orbit of Km naught through M in capital M. Theorem 3. Let M be an oriented Riemannian 2 manifold. Suppose for some m naught element of capital M, phi from Km naught to S1 is surjective. Then, in a geodesic coordinate neighborhood of m naught, the geodesics through m naught are the orthogonal trajectories reparametrized by arc length of the orbits of Km naught. See figure 1. Proof. If capital G from d epsilon to m is a geodesic coordinate neighborhood of m naught, then the orbits of Km naught are the images under G of the concentric circles about the origin in d epsilon. You can refer to the proof of the previous lemma. These orbits are orthogonal to the radial geodesics by Gauss lemma. By the uniqueness of orthogonal trajectories, these trajectories are the radial geodesics. Let us see an example now. Example 1. Consider the plane R2 with the usual Riemannian structure. Since norm dou by dou R1 is equal to 1, the map C from R2 to S of R2 given by C of M is equal to M comma E1 is equal to M comma dou by dou R1 is globally defined. So, the special connection K1 is defined on all of SR2. Moreover, E1 is equal to dou by dou R1 and IE1 is equal to dou by dou R2. So, omega 1 dash is equal to dr1 and omega 2 dash is equal to dr2. Thus, omega 1 is equal to cos theta omega 1 tilde plus sin theta omega 2 tilde, which is equal to cos theta pi star dr1 plus sin theta pi star dr2. Similarly, omega 2 is equal to minus sin theta pi star dr1 plus cos theta pi star dr2. Since phi 1 is equal to d theta, the first structural equations become d omega 1 is equal to minus sin theta d theta meet pi star dr1 plus cos theta d theta meet pi star dr2, which is equal to phi 1 meet omega 2. And similarly, d omega 2 is equal to minus phi 1 meet omega 1. Thus, structural equations are in the simplified form, and by uniqueness, the special connection on SR2 is the Riemannian connection. Moreover, as we have seen for the special connection, d phi 1 is equal to 0, so the curvature K of R2 is identically 0. Clearly, Each translation and each rotation of R2 is an isometry. Let K1 be the group generated by rotations and translations of R2. Then K1 is transitive. In fact, the group of translations is transitive. And phi from K1 naught to S1 is surjective. K1 naught is group of rotations about 0 in R2. So by theorem 2, K1 is the full group of isometries of R2. For M naught element of R2, Km naught is the group of rotations of R2 about M naught. Since the orbits of Km naught are circles about M naught, the geodesics through M naught are straight lines by theorem 3. We will see another example. Example 2. Let S2 denote the sphere of radius r about the origin in R3 with the induced Reimannian structure. Note that the group K of rotations about the origin in R3 is a group of isometries of S2. It is the full group of isometries of S2 by theorem 2. Since K is transitive on S2, the curvature K of S2 is constant by theorem 1. By the Gauss-Bonnet theorem, 1 by 2 pi integral over S2 K volume is equal to psi of S2 which is equal to 2. That is, K volume of S2 is equal to 4 pi. K is equal to 4 pi by volume of S2 which is equal to 4 pi by 4 pi r square which is equal to 1 by r square. The geodesics through M in S2 are the orthogonal trajectories of the orbits of the group of rotations of R3 that leave M fixed. These orbits are circles about M. So the geodesics through M are the great circles through M. See figure 2. Example 3. Let D denote the open disk of radius 1 in R2. Regarding D as a subset of complex plane, consider the Reimannian structure called the Poincare or hyperbolic or metric on D defined by inner product V1 V2 is equal to V1 dot V2 by 1 minus P bar the whole square, where V1 V2 element of T of D comma P, where P is an element of capital D, where V1 dot V2 denote the usual inner product or the dot product on T of D comma P, and P bar is the complex conjugate of P. So that P bar is equal to R square, where R is the Euclidean distance from P to the origin. Thus, norm dou by dou R1 at P is equal to norm dou by dou R2 at P, which is equal to 1 by 1 minus P bar. And inner product dou by dou R1 dou by dou R2 is equal to 0. Note that the radial lines in D through the origin have infinite length. For if alpha from closed interval 0 1 to D is given by alpha of T is equal to T e raised to I theta for some theta, then L alpha integral 0 to 1 norm alpha dot T dt is equal to integral 0 to 1 by 1 minus T square dt, which is equal to infinity. Let C be equal to f from D to D, where f of z is equal to e raised to I theta into z minus p by 1 minus zp for some p element of D, where 0 less than theta less than 2 pi. From elementary complex variable theory, C is a group of transformations of D onto itself, that is in fact a group of isometries of D. For let f element of C, if we identify T dz with T of dfz by identifying both with R2 in the usual way, then since conformal maps preserves angles, dfz is equal to lambda of z gz for some real number lambda of z greater than 0 and some rotation g of z element of S1. The magnification factor lambda of z is given by lambda of z is equal to mod df by dz of z. But an elementary computation shows that mod df by dz of z to 1 minus zz dot is equal to 1 minus f of z bar. Since vectors at V, which are unit vectors in the Poincare metric, have Euclidean length 1 minus zz bar, this implies that df of z is a rotation which maps unit vectors in the Poincare metric into unit vectors. That is, df of z is an isometry for each z. So, f from capital D to D is an isometry. Let C is a group of isometries of D. C is transitive because for p element of D, fp from z to z minus p by 1 minus zp bar maps p into the origin. Hence, for each pair p1 p2 element of D, fp2 inverse composite fp1 maps p1 onto p2. Moreover, the isotropy subgroup K0 of C at the origin is given by K0 is equal to f from D to D, where fz is equal to e raised to I theta into z. That is, K0 is the group of rotations in R2. Hence, phi from K0 to S1 is surjective. So, by theorem 2, C is the full group of isometries of D. In particular, since C is transitive, the curvature K of D is constant by theorem 1. Since the isotropy group K0 at 0 is the rotation group whose orbits are the circles about 0, theorem 3 tells us that the geodesics through 0 are the radial lines, suitably parametrized. Since isometries map geodesics into geodesics, and since the image of a radial straight line under a conformal transformation of D is either a radial straight line or a circle which meets the boundary of D at right angles, we see that such lines and circles are the geodesics in D. See figure 3. In particular, the sum of the interior angles of a geodesic triangle in D is less than pi, so that by the Gauss-Bonnet theorem, the constant value of K is negative. See figure 4. Let us note these important points. First one, although we have exhibited the hyperbolic space D as a submanifold of R2, note that the inclusion map is not an isometry. In fact, it can be shown that the space D cannot even be embedded as a Riemannian submanifold of R3. Second point, we have exhibited three Riemannian manifolds R2, S2 and D of constant curvature K equal to 0, K greater than 0 and K less than 0 respectively. It turns out that any two simply connected complete Riemannian 2 manifolds has constant curvature. These three examples are important in several different mathematical disciplines as illustrated in the table 1 given. So, in the table you can see for the space R2, the constant curvature K equal to 0, group of isometries is the Euclidean motions in R2, rotations plus translations. It is a complex plane in Euclidean geometry. Similarly, you can see for S2 and D. Relative to the last column in particular, these three examples are the only elementary geometries. Under the replacements, points goes to points, straight lines goes to geodesics, length goes to arc length, angle goes to angles and congruence goes to isometry. Most of the axioms for Euclidean geometry are satisfied by these examples. The most noteworthy exception is that Euclid's fifth postulate, the parallel postulate, fails to hold on D. That is, given a straight line L and a point P not on L, there are infinitely many straight lines through P which never meet L. See figure 5. In the case of elliptic geometry, it is customary to use P2 as model rather than S2, so that any pair of straight lines will meet in at most one point. In this elliptic geometry, a straight line fails to divide the remaining points into two disconnected paths. In the case of complex variable theory, R2, S2 and D are the only simply connected complex 1 manifolds, a strong form of Riemann's mapping theorem. Before we conclude, let us summarize what we have learned in this session. We started our discussion with the properties of isometries on manifolds that preserves Riemannian structure and orientation. That is, it preserves the curvature, Riemannian connection and parallel translation, and it maps geodesics to geodesics. We have discussed the proof of a theorem which says that if a group of isometries on a manifold is transitive, then it has a constant curvature. We have discussed two more theorems on isometries of a manifold and a lemma required for this proof. We have also discussed a few examples on the topic. These are some exercise problems which you can try out for a better understanding of the topic discussed in this session. First one, find the constant value of K discussed in example 3. Hint: K can be found either by computing the area of a geodesic triangle and applying the Gauss-Bonnet theorem, or by use of Jacobi's equation. Second problem, show that two spheres of different radii in Euclidean space are not isometric to each other. Third one, in Rn+1, consider the non-positive definite metric given by h of uv is equal to minus u0 v0 plus u1 v1 plus etc. plus un vn. Consider the set Hn, which is equal to the set of all x element of Rn plus 1 such that h of xx is equal to minus 1. Consider the point p equal to minus 1, 0, 0, etc. 0 element of Hn and the map phi from Hn to B1 0, which is a subset of 0 cross Rn, where phi of x is equal to p minus 2 into x minus p by h of x minus p x minus p. Show that phi is a diffeomorphism into B1 0, and if we consider the metric h bar is equal to 4 by 1 minus mod y square the whole square into delta, delta being the Euclidean metric on Rn on B1 0, then phi star h is equal to h. In other words, phi is an isometry between the unit ball model and the hyperbolic model for hyperbolic space. These are some books for further reading. Introduction to Differential Geometry by J. A. Thorpe by Springer-Verlag. Second one, Lecture Notes on Elementary Topology and Geometry by I. M. Singer and J. A. Thorpe, Springer-Verlag 1967. Third one, Elementary Differential Geometry by B. O. Neal, Academic Press 1966. Fourth one, Lectures on Differential Geometry by S. Sternberg, Prentice Hall 1964. Fifth one, Differential and Reimannian Geometry by D. Lowitz, Academic Press 1965. Sixth one, Reimannian Geometry by S. Gallot, D. Hulin and J. Lafontaine, Springer-Verlag 1987. Seventh one, Reimannian Geometry and Geometric Analysis, 4th edition by Jürgen Jost, Springer-Verlag. Thank you for watching this session. We will meet in another session with another topic. Till then, goodbye.